Okay. I believe we were talking about the Dirac Lagrangian, and is it not normal for graduate classes? It's not classes, right? Anyway, so. So the way we have been talking about the Dirac spinner is to split that into left and right-handed wild spinners, and so that's how we started. But what we'll end up doing is to primarily work with the Dirac version of the equations and the Lagrangians. Right? So let me just write down the two equivalent ways of writing the Dirac Lagrangian. So I'll use Paskin and Schroeder's notation. So our side left, this is Paskin and Schroeder, is what we have been calling lambda, the spinner lambda, right? Lambda for left. And side right is what we call rho for right R. Right? So side left dagger, I sigma bar, mu, and then now I'm just going to go ahead to use the covariant derivative because we're going to do QED. So it's going to be partial mu minus IE, A mu. So that's the covariant derivative acting on side left. Okay. So if it were a massless particle, this would work well for the left-handed wild spinner because it's a Lorentz invariant. And we have discussed this before, and we've seen it explicitly for the scalar, that if you have a Lorentz invariant Lagrangian, you are guaranteed to produce a Lorentz covariant equations of motion. Okay? And then we will have the right-handed guy. The right-handed guy is the one with sigma mu, partial mu. This is d mu. Right? So maybe I'll just write down as d mu. Already telling me I shouldn't do this. There we go again. Every time I come, I'm struggling with my examples. This is the d mu. D mu is this guy. Side right. And as we've discussed, is the mass term that breaks, sorry, I shouldn't say break, mixes, couple the left and the right-handed wild spinner. So it looks like this minus m, side left dagger, side right. So this is a Lorentz invariant, but you notice that if you write this down, it's not permission. If you think about it in terms of operators, it's not permission because when you take a dagger, you don't get back itself. So you, in fact, are kind of compelled to write down the counterpart, right? And so in this case, it seems like there's a relationship between parity and permissivity, because if you only write down one of them, it's not parity invariant as well, right? And so parity and permissivity actually comes together once you promote it to an operator. But anyway, here is exactly where the left and the right gets mixed. And if you look at the dimensions, the dimensions of this guy will have to be a mass term. And in fact, this is going to be the mass of our electron, or muon, or quark. All of these fermions would have this sort of interaction with the electromagnetic current, at least. The situation for the weak interactions is a bit different. But we have seen that all of this can be packaged into something a bit more compact, which is using the 4-component notation. Right? And this will be sigma bar, and then I, d slash, minus m, psi. Okay? And again, d slash is gamma mu, d mu, and psi bar, remember, means psi dagger gamma 0. Okay? This gamma 0 is here because gamma 0 times gamma mu produces exactly these two terms. Okay? So this term and this term is exactly gotten by having gamma 0 times gamma mu. Otherwise, you won't be interacting left and left, right and right. Okay? Because gamma mu itself is off diagonal. Remember, gamma mu is given by, in the chiral basis, given by gamma bar, sigma bar mu, 0, 0, 0. Okay. So what we haven't done, so we discussed this the last time, and so hopefully by now you can see this gauge invariant, it's Lorentz invariant, and it's also U1 gauge invariant. And again, invariance means that, in this case, it means that psi is replaced with e to the I, e theta, which can depend on space-time, psi. And as long as A is also shifted by a gradient. Okay. And then it's U1 gauge invariant and Lorentz invariant. So that's why you're guaranteed that equations of motion are also gauge covariant and Lorentz covariant. Okay. So what we haven't done is to actually vary the action that comes from this guy, and looking at how the Dirac equation actually emerges from here. Right? So let's in fact do that. So psi, S of psi, is now the integral of d4x, and then it will be psi bar I d slash minus m psi. Okay? And we're going to demand that the variation of psi is 0. So here's a little tricky point, which is that psi is complex. Okay? So because it is complex, and because right now it's arbitrary, I claim I can either vary psi or psi dagger independently. So because psi is complex, we can vary psi and psi dagger independently. So this is just because they are arbitrary. So I can choose, it's kind of like choosing bases. Right? So z, for example, look at a complex number. Z is equal to x plus iy. Okay? And z star is x minus iy. Okay, so I can vary, if I say I want to vary z, I can say, okay, I can vary x and y independently, and you wouldn't complain about that. But you see that I can think of z and z star as my two independent variables, right? Because, for example, z minus z star over 2I is y, and z plus z star over 2 is x. So in other words, I can get from z star, I can get x and y independently. So therefore, I should be able to view z and z star as independent variables. In fact, the theory of analytic functions is in fact the statement that of the two independent variables, only z shows up, right? That's basically the theory of analytic functions. And once you are sure that all your functions only depend on z and not z star, then there are a lot of nice properties about such functions. Okay, so that's an example. So anyway, this is just to say that we can now go ahead and vary. For example, let's do psi star first because it's very easy. If you vary s with respect to psi star, I want it to be stationary, right? Yeah, stationary action. Means this, and what it means in particular is this gives me the integral of, remember psi bar is in fact psi dagger. So you now have delta psi dagger, gamma 0, and then I d slash minus n psi. Well, that's easy enough. So if this is an arbitrary variation, then and it's supposed to be 0, that means this guy better be 0. This guy better be 0. But that's exactly the Dirac equation. Okay, so that's easy enough. The other one is a bit harder, but you'll get the same result. Okay, but we'll do that because we should start to get a little bit more familiar with the manipulation of these Dirac matrices, right? Because that's what you're going to end up playing around with when you calculate scattering amplitudes. Okay, so let's also do the other one. Delta psi s equals to 0. Okay, so that basically tells you that you have an integral over x, and then now you have psi bar. You don't need to vary it because that's dagger, and then I d slash minus m, and then delta psi. Okay, and then now, well, you have a derivative acting on delta psi. So I'm going to integrate by parts. So this is d4x. Actually, let's write it out more explicitly first. This is d4x, and then psi dagger, gamma 0, gamma mu, and then partial mu. Sorry, there's an I here, right? So let's be careful. And so there's an I, partial mu, plus E a mu minus m psi. Okay. So what I said just now was I'm going to integrate by parts this partial derivative, and this is going to give me, let's just do it systematically, minus I mu psi dagger, but this is also this is just a real object, right? So I can pull it out, I can simply pull it out if I want. So let me do that. So minus I partial mu plus E a mu, all acting on psi dagger. Okay? Again, this is just a real object. I have to just pull it out. It's not a matrix, right? It's not a matrix. If it's a matrix, I have to be a bit careful of how I do it. And furthermore, this is minus I, so I can actually just do the following. I can just say that this is now the covariant derivative acting on, actually this is I times the covariant derivative acting on psi, and then the whole thing dagger, right? The whole thing dagger, I can simply do that because all that's going to do is going to flip the sign of I, okay? So I've integrated by parts, gamma 0 psi. And then let me not forget my mass term, minus m sine dagger gamma 0 sine. Okay, that's what's happening. I'm sorry, that's also the gamma mu sine. Right, so all I've done is I integrate by parts, but I shouldn't forget my gamma mu sine. Okay? But now, let's in fact do the following. I'm going to erase a little bit of this because I want to observe some properties of the gamma matrix. And I'll talk a little more about it after the Dirac equation as well. So, what is gamma 0 gamma mu? Okay, so I've already said that this combination is what gives us the left-handed and right-handed kinetic term, basically the part that has derivatives, covariant derivatives. So we should expect that this will be diagonal, right? But let's write it out just to be sure. So gamma 0, according to this, is just 1. Identity, right? Remember, these are 2 by 2 blocks. 0, 0. That's gamma 0. And then gamma mu is sigma mu bar, sigma mu, 0, 0. And all you have to do is just multiply them out. So 0, 1, sigma mu bar, and then 1, 0. So it's 0. And then this is 0, 1, 0, 1, 0, so sigma mu. So indeed it's diagonal, and that's exactly what's going to give us the coupling. If you sandwich the gamma 0 sigma mu here, that's exactly what makes left-handed dagger left-handed, and right-handed dagger right-handed. Right? That's exactly what's happening. But this is also permission. It's Hermitian because the sigma matrices are Hermitian. So that means that gamma sigma gamma mu dagger is in fact equals to itself, which in turn means if you just take the dagger of this, tells you that it's gamma mu dagger gamma 0. Okay, so it just means it's AB dagger is B dagger, A dagger, but it's equal to itself. So I can certainly make this replacement over here. Okay, so what I have over here is therefore the following. I have now I can now move it into, let me just do it systematically. So this, remember, is ID slash psi dagger. And now I know I can write it as gamma mu dagger, gamma 0 psi, okay, and then minus m psi bar psi. Okay? But that also means minus m psi dagger gamma 0. But that also means I can now take this as a, I'm sorry, not that, d slash d mu gamma mu. And then now it means that I can write it as gamma mu I d mu psi whole thing dagger, right? This is exactly what, this is AB, B dagger, A dagger is the dagger of AB, okay? And then gamma 0 psi minus n psi dagger gamma 0 psi. I'm sorry, I already lost my delta psi, right? If I make a boo-boo, you should point out that I made a boo-boo. This is delta psi. This is delta psi. Delta psi. This is delta psi. Delta psi. Delta psi. And then finally, you have the following. You have d for x, I d slash minus n, whole thing acting on psi. Then you take the dagger of that thing, and then gamma 0 delta psi. Okay. So remember what we're trying to do is we're trying to vary psi, not psi dagger. So at the end of it, what you see is that up to a surface term, when you integrate by plots, there's a surface term. You will have basically the left-hand side of the Dirac equation dotted into a small but arbitrary variation, right? So for this thing to vanish, therefore the whole thing here must be 0. Otherwise, it's not going to vanish. But that being 0 is, again, just a Dirac equation. Just a Dirac equation. So again, we discover that either varying psi or psi dagger gives you the Dirac equation. But you see that if you vary psi is more work, right? You have to integrate by parts. You have to know some properties about the gamma matrices and so on. But I want to show it because later on we need to do a bit more gymnastics with these kind of matrices.
Does this mean psi and psi dagger are not independent variable because we get the same?
Only after you vary them. Only when they're on shell, then of course they're not independent, right? If you solved it, you found a solution, then of course they're not independent, right? But before you vary them, they are completely arbitrary. Just like I was saying, that's why I mentioned the analogy with complex numbers, right? Z is x plus iy, and if I tell you it's completely arbitrary, then you can treat z and z star as basically independent variables, just as x and y are independent variables, right? Yeah, it's just a change of basis. Either you use z star, or you use x or y, x and y, right? That's the idea. So as far this is as far as varying the action is concerned, right? But once you have the equation, which is the same, obviously, right? It gives you the same equation. Once you solve it, then of course the solution is fixed, and they're not independent anymore, obviously, right? Yeah. And it also depends on how you vary it, because we're about to do the U1. So, for example, in fact, I wrote it down. So if you rotate psi, then I think you are compelled to rotate psi dagger as well, right? Otherwise, I don't think it's consistent, right? This is basically like rotating a complex number, and if you rotate it in one way, the dagger has to be rotated the other way. The complex conjugate, yeah. So it depends on how you vary it. But if it's an arbitrary variation, then I think you're allowed to vary them independently. But this is a very specific kind of variation, right? You're rotating in a very particular way. Yeah. So it depends on how you vary it, but in principle, you can treat them as independent variables.
How do you do the integration by part in the second?
Come again?
How do you do the integration by part in the second?
Why? Why or how? 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 Just integrate by parts, right? So if you have it's not even specific to spinors, right? It's just if you have partial mu mu, right? So this is a divergence, A, and then the integral like that. Then this is equals to a surface term minus integral partial mu A B mu.
But there's no minus sign.
Because there's a dagger here. Yeah, I skipped one step. Let me write it down, okay? So let me focus on this term here. Let's do it here. Yeah, just to be clear. But basically because there's a dagger there. So let's just focus on the term where I have psi dagger gamma 0 gamma mu I partial mu psi, right? So I have a term like that, actually delta psi. Keep forgetting delta psi, right? Now I'm going to integrate by parts, and this is going to give me minus I partial mu psi dagger gamma 0 gamma mu delta psi, right? But because I want to view this thing as operating on psi, I will now write it as I partial mu psi, and then the whole thing dagger, right? Gamma 0. In fact, I also know that this is Hermitian, so I want to write it as gamma mu dagger gamma 0 delta psi, and then I combine it, and then I moved it over, right? Because this is B dagger, A dagger, so this is therefore AB, which is gamma mu I partial mu psi, whole thing dagger gamma 0 delta psi, right? That's how you do it. So the I when you take the dagger, it's just a complex conjugate. So that accounts for the minus sign.
But EMU is
It's real, right? A mu is real. So you can take the dagger all you want, right?
Originally it's time with delta phi.
Yeah. So remember, this is a real object that is not a matrix, right?
Oh.
This is not a matrix, right? So you can move it anywhere you want. Right?
Oh yeah.
Yeah. Yeah. Good. Yeah, you should always you're not clear. Yeah, there's a lot of, I understand, right? The first time you learn field theory, it's all kinds of notation that takes some time to get used to. So yeah, it's not clear this aspect. Okay, so good. So we have seen the Dirac equation and how it emerges from the Lagrangian. And again, I emphasize that you would I had a question the other day, right? How do you know how to write down the Lagrangian? So the guide again is that the Lorentz invariance, and in this case, because I want to have electromagnetism, I want gauge invariance as well. So that's a guide, and that's what's happening to this Lagrangian. There's both gauge and Lorentz invariant. I want to point out a subtlety that I don't know if I haven't seen it in Peskin and Schroeder, but there's a subtlety about this action principle which I should have mentioned when I integrated by parts. But let me do it. Let me do it here. Okay, so let me erase this and let me do it over here. I don't have an answer to it. I want to point out a subtlety. So you guys can think about it and tell me the answer when you guys figure it out. So when we did scalar field theory, let's just do a master scalar. Okay, let's just do a master scalar. What we did was when we varied the action, we realized and we integrated by parts. we specified, what we did was we specified the field on some initial surface and some final surface, right? So this is Ti surface, this is Tf surface, this is time, and this is space, okay? And so if I assume that that is true, meaning I have been given the initial and final field configurations, then I'm all good, right? What I mean by that is that I will have, when I integrate by parts, the following. I will have delta phi, and then I will have a minus sign, and then partial mu phi, sorry, no minus sign. And then I will have d3 sigma mu. And this will be an integral on the boundary. Okay, so if you remember this discussion, plus actually now minus the delta phi, I think it's 1/2, and then partial squared phi. Okay. So the reason why this is important, that boundary conditions are important, is because if you fix the initial and final fields, I've said already that that implies that the initial variation must be 0, and the final variation must also be 0. The variation at this boundary is 0. And that's what makes this surface term vanishes. Okay. But let's see what happens for the Dirac equation. Okay, the Dirac equation is nothing like that. The Dirac Lagrangian is nothing like that. Because while the scalar field theory has two derivatives, the Dirac Lagrangian has only one derivative. Okay, so for simplicity, let's do the delta psi dagger, because delta psi is very complicated. So let's do that. So let's vary it, right? So we get delta psi dagger, gamma 0, I d slash minus m psi. And you notice that there's nothing. It's just, if you want this to be 0, this will be 0, right? It doesn't say anything about the initial and final conditions. A little bit strange if you write it this way, right? If you vary psi, you will have to integrate by parts once. And the boundary, so you will have a boundary term in that case, but then you also have a problem. When you integrate by parts, so if you vary psi instead, what you have instead is you will have a term that goes like a psi dagger, and then gamma 0, and then gamma mu, right? And then I, and then psi, delta psi. And this term will be integrated on the boundary plus dot dot dot. But this is the boundary term. Okay. So that's even worse. Why is it even worse? Because remember that because it's a first order equation, you only need to specify boundary conditions on one surface, either this surface or this surface, but not both. Not both. So how do you guarantee that delta psi vanishes on both surfaces? If it doesn't vanish, then you cannot say it's stationary. Right? Anyway, think about it. Tell me the answer. Okay, so now I'm going to talk about Noether's theorem. Okay, we talk about the Dirac, the Lagrangians for scalars, for electromagnetism, Maxwell's fields, and for Dirac. So now we're ready to talk about Noether's theorem. And this is, in fact, one of the biggest reasons why we need to talk about Lagrangians at the classical level. Obviously, at the quantum level, it will become indispensable for many purposes. Particularly when we do path integrals, it will become indispensable. We have to know the Lagrangians. Any questions for me? Oh, before we do that, I want to say a few more things about the Dirac. So before I forget, so the gamma. So remember the gamma matrices obey the Clifford algebra. And what it turns out that you can show that you can form a basis. So remember these guys are 4 by 4. So the space of 4 by 4 matrices form a 16-dimensional vector space. Right. So those of you who are taking quantum mechanics with me will know that hopefully quite well. That's one of the first examples of the vector space that we talk about. And so furthermore, we know from the discussion of left-handed and right-handed wild spinners that we know actually separately they transform as Lorentz 4 vectors. So if you look back at the discussion, so even though these guys transform as SL2C, once you sandwich it between, once you sandwich it with sigma bar and sigma, these guys are Lorentz 4 vectors. So you can add them together, and in fact, this is the this will be a 4. This will be a 4 vector itself, and this, in fact, you would find is of course nothing but sigma bar gamma mu psi. Sorry, I keep saying sigma. Psi bar gamma mu psi. Okay, so this is in fact equal to this guy. So this in fact is also Lorentz 4 vector. So, but this is only one possible matrix out of the 16 that we can construct. So it's good to kind of pause and just enumerate all the possibilities. It's a 4 vector, so naturally you can expect that you can now construct higher rank tensors from this, right? And again, this is important if you want to know how your spinners, how to form tensors. If you ever need to construct higher rank tensors in your Lagrangian, right? So how do you do that? So you have to take note of the fact that these guys basically anti-commute, right? So when mu and nu are not equal, they anti-commute. So what it means is that the arrangement of the product of distinct gamma matrices don't really matter because you can always just anti-commute them, right? If they're not the same, you can just anti-commute them, right? So for example, the first guy that I'll talk about is something called gamma 5, and it's I times gamma 0, gamma 1, gamma 2, gamma 3. Okay, so if you look at Pascal and Schroeder, they define it as a contraction with the Navier-Stokes symbol. But I think that's not necessary, right? Because, again, because it's because of the anti-commuting properties. All of these are distinct, so I can swap them around all I want. The only difference is it will cost me some minus signs. So I can write this as gamma 3, gamma 0, gamma 1, gamma 2, but that would just be minus gamma 5, right? So if this is the definition, I'll stick to it, and this will turn out to be, in fact, equals to minus minus identity and identity. Okay, let me just make sure I got my signs right. Yes. And this object itself anti-commutes with everybody. So gamma 5 anti-commutes with everybody. Something that we'll use in a little bit when we talk about chiral symmetry. Okay. So let's return to this discussion. So how many matrices? So this is one possibility. So therefore you can write down, for example, gamma bar, gamma 5 psi, okay, which is to be distinguished from psi bar psi. Okay, so this is 1, that's 2, that's 3. You can think of this as the identity, right? This is, okay. All of these are different, let me emphasize. Okay, so gamma mu is different from gamma 5, which is of course also different from I. But what about the other guys, right? So this guy is like a rank 4, actually this is like a rank 4 tensor in the sense that these are all, you can basically anti-symmetrize them. Yeah, so this is a rank 4 tensor actually. Even though I call it gamma 5, it's really a rank 4 tensor because you can just write down mu alpha beta and you discover that as long as they're all distinct, it's all going to be proportional to gamma 5. But what
is the single component of that rank 4 tensor or
single component of what tensor?
Inside the tensor.
This is a matrix.
Yeah, I mean the matrix is that one single component of that rank 4 tensor, or itself is a.
This is the definition. You're asking me what is gamma 5, right? Are you asking me what is gamma 5? Gamma 5 is the product of gamma 0, gamma 1, gamma 2, gamma 3 times I, which I claim, if you look it up explicitly, will give you this guy.
It means, if the rank 4 tensor you mentioned is
by rank 4, I mean that there are 4 indices here.
Yeah.
Right. It's actually the dual of, so let me just say this is actually 1 over 4 factorial times I, epsilon, mu alpha beta, gamma mu, gamma nu, gamma alpha, gamma beta. Right? This is a rank 4 tensor. Right? But because of the anti-commuting properties of the gamma matrices, you find that you can just take the contraction. In other words, the rank 4 tensor really only has the 0, 1, 2, 3 as the distinct matrix, right? Everything else, every other non-trivial rank 4 tensor is proportional to that, right? And so all I'm saying is that therefore you can just contract it with the Lagrangian and just call it gamma 5. Yeah. So it's just one. Just think about it. Just think of it as just a product of these matrices, right? And if it confuses you, don't worry about this rank 4 thing. It's just saying that I'm just trying to now construct all the 16 independent matrices that can exist for 4x4 for the space of 4x4 matrices. The reason why I'm mentioning rank 4 is because it says something about the transformation properties. It turns out that this is a pseudo-scalar. Let me just write it down. Pseudo-scalar. This is a scalar. And by scalar, it's a Lorentz scalar. So if you do a Lorentz transformation on the left, on the Dirac spinner, you'll find that this is a scalar, this is a pseudo-scalar, which means that under Lorentz transformations will all be invariant. But if you do a parity flip, then this will be invariant, but this will give you a minus sign. Okay? Let me write it down first, and then I'll write down these guys, and then I'll tell you guys more about it. So there's 1, 2, 3, and then you can write down the rank 2 guy, which is just the anti-symmetric. Just gamma mu, anti-symmetrize it. Okay, and then this guy is anti-symmetric, right? So you have how many independent mu components? So you have 4 squared minus 4 divided by 2. So this is 16 16 minus 4, 12 over 2 is 6. Right? So there's 1, 2, 3, and then that's 9. Right? And then now we will need the last guy, which is gamma mu, gamma alpha, anti-symmetrize. Is that how he writes it? Yeah, so it turns out that this guy, again, because of the anti-symmetric properties, we don't write this down. In fact, this is actually dual. In other words, it contains the same information as, in fact, psi bar gamma 5. I think people usually write it the other way. Gamma mu, gamma 5. Okay. There's a correspondence between them. How do you go from one to the other? Just contract it with the Lagrangian symbol. So let me write it here. So if you write down gamma bar, psi bar, I don't know why I keep saying gamma bar, psi bar, gamma mu, gamma alpha, psi, and if you contract it with the Lagrangian symbol, mu, alpha, beta, okay, so this will be proportional. I'm not going to bother with the numerical factors. This is going to be proportional to psi bar, gamma beta, gamma 5, psi. Okay. And the reason why we can do that is because the Lagrangian symbol is invertible. You just multiply both sides by Lagrangian, and then you can, once I give you this, you can give me this. Once I give you this, you can also give me this. So it's kind of invertible. And that's why people usually work with this. Okay? And so, how many do we have now? Sorry, we have 4 here, right? We have 1 here, 1 here, we have 6 here, and we have 4, right? So how many do we have? 8, 10, 14, and 16, right? So that's basically the basis. Okay, so this guy, this guy, this guy, this guy, and this guy. These are the 16 possible tensors that you can write down using Dirac spinors, bilinears, I should say. Of course, you can do more by multiplying them together, but these are using bilinears, right? So let me just write down what I was saying just now. So this guy is a vector under space-time transformations as well as parity, right? So gamma I in particular, that guy will go to a negative of itself if you do a parity flip. What you find is that psi bar gamma mu gamma 5 is a pseudo vector. What it means is that it behaves like a vector except when you do a parity flip. When you do a parity flip, it won't change sign. So it's kind of like a magnetic field, right? So if you guys remember, the magnetic field doesn't change sign when you flip your axis. when you put the X, it doesn't change sign. And so, yeah, and so it's all because of this gamma phi, okay? And then you have gamma nu antisymmetrized, and that's just a rank 2 tensor. It's a rank 2 tensor under, of course, antisymmetric, right? Because the mu indices are antisymmetric. And it's an honest antisymmetric tensor under parity and space-time transformations. And then we do gamma, then we do the scalars. So this is a scalar, an honest scalar under Lorentz, parity, and so on. And then this is a pseudo-scalar. Which means under parity, it will go into negative itself. So under parity, let me just write it down just to make sure. Under parity, it actually goes into negative itself. Okay? Unlike this guy, which doesn't happen, it's just invariant. It just remains itself. Okay? But this is a pseudo-scalar. And you can remember, this is a pseudo vector because it is a gamma phi. So because this is a gamma phi, it's a pseudo scalar. And will I capture everybody? Gamma phi. 1, 2, 3, 4. Yeah, I think I have here 4 plus 6. That's 10, 14, yeah, that's good. Okay. So those are the transformation properties that we want to keep in mind. In particular, maybe I should say this, since I'm talking about this, we will discover that, in fact, this is proportional to the electric current. I say proportional because you need a charge here. It's proportional to the electric current or the number current or the fermion current, right? Or the fermion current. Fermion number current. Okay. So and it makes sense because this is a 4 vector, right? And what we'll discover is that the divergence of this guy, if you evaluate it on the solutions, will in fact be 0, right? And that's what you expect. If there's a conservation of electric charge, conservation of fermion number, it better be divergence free. And on a more fundamental level, we'll see very soon, this is in fact due to U1, global U1 symmetry, right? So after the break, we'll talk about that. But I also want to mention that this current, so this current is what couples to the vector potential. Right? So if you guys remember, when we talk about Maxwell Lagrangian, we said that the Maxwell field itself has a Lagrangian of S squared. And then we said that the current must couple to the electromagnetic field in this way. And this is exactly what happens in the Dirac Lagrangian. Right? So remember that the Dirac Lagrangian looks like this. And if you expand this out, you would see that the A term here is exactly this, right? And this is exactly of this form. Okay? I just want to highlight this point. And so whenever you have a current, or whenever you have a gauge field, the green bosons, the Z bosons, the gluons, and the electromagnetic vector potential, you expect this kind of coupling between the vector potential and the current. the only difference is that when you talk about non-abelian gauge theory, there will be additional indices. There will be a cover index here, and there will be a cover matrix here as well. So that makes it a bit more complicated. But otherwise, the structure is the same. This A mu J mu term is telling you that you have a current and it couples to your gauge field, and that's what mediates the interaction between the charged current and the force field. The force field meaning the A, right? Yeah. Maybe we should take a break first, and then we'll come back to continue the discussion. Any questions? No? Okay, let's take a break for 10 minutes, and then we'll come back. 1:10, right? Sorry, 2:10. That was 2 o'clock. 2:10. Let me just continue with what I wanted to say here, but I took a break. So I got this question of, do these things show up in electromagnetism? Or the more general question is, which ones show up in the standard model of particle physics? Right? That's the more general question. So I won't give you a full answer, because the full answer would have to necessarily involve non-abelian gauge theory, which I don't know if I have time, but I hope in a few weeks I'll come back to talk about it briefly. But basically, for electromagnetism, what couples to the electromagnetic field must be a genuine space-time vector. Right? So this must be a space-time, a 4 vector. Otherwise, you will be breaking Lorentz invariance. Right? If it were not a space-time vector, you will break Lorentz invariance. But it turns out that the weak interactions, in fact, gives you things like the pseudo vector. In fact, it's a mixture of. Let me just write it down. So for the weak interaction, it turns out that the W's and the Z's and so on, in fact, couples to not the 4 vector current, but it actually couples to. So let me just say it's a squiggle because I don't want to be inaccurate, but it basically goes like this. It only couples to the left-handed part of the current. Okay, so this actually turns out to be W mu psi left dagger gamma mu bar sigma mu bar psi left. This is what happens. But if you use the notation that we're using here, you write it as 1 minus gamma phi. Okay, and the same thing for Z's, and that's what happens. That's the kind of coupling that they have. So this was a shock to theoretical physicists in particular back in the 50s and the 60s. People were wondering whether parity should be preserved, because, like I said, once you have a gamma phi, that tells you that it's a pseudo vector. It's no longer a. So why should parity be violated maximally? Because when you do a parity flip on this, you get a right-handed guy, but the right-handed guy is not here. So it violates parity in a maximal way, so to speak. And as you know, the building, our building, the building that we're in, is named after Professor Wu, who in fact was the first person, I believe, who set up an experiment to verify this claim that the weak interactions could violate parity. Where I think she looked at some cobalt decay, and then it came out only in one direction. And so it violated parity in a very dramatic way. So that's why we honor her, because she was the first person, first group she met the first group to make this discovery. So this was, in the old days, theorists had, I would say, theoretical bias, right? They think that everything should be symmetric. And so certainly should be parity symmetric as well. And so they would have thought that it should just be probably just a regular full vector. The current that interacts with the W and the Z's should be just a full vector, but it turns out to be no. It's just not true, right? So yeah, so that was quite dramatic back in the days. And at the level of an effective interaction, I don't know if Pascal Schroeder talks about it, but if you guys look at the, maybe later on I'll talk a bit more about it, but if you guys look at the book by Griffiths on particle physics, he talks about how we can construct an effective operator, something of this sort, that describes neutron decay. So the decay of a neutron is also mediated by the weak interactions. But the neutron is a messy object, right? It's not just a pure one fermion. This is, bouncy of fermions with gluons and so on. So it's a little bit messy to describe it, but you can talk about decay by constructing an effective operator, except now it's not 1 minus gamma phi, but there's a number here, and then there's also a number in front of gamma phi, and you can describe this kind of nuclear decay of spin half or fermionic hadronic states by writing down operators like that as well, right? So this is the other example where you get this kind of parity violating interactions. The other guys, like especially this higher rank tensor, if you want to introduce something like that in your Lagrangian, then you see that you will have to contract the two indices with something that also has two indices. Because remember, the Lagrangian has to be a Lorentz scalar, right? So usually what you'll find is that whatever that you contract it with will not occur in ordinary electromagnetism, right? But it can, in principle, show up in more exotic theories. But I'll say there's also another constraint from quantum field theory that I hope to talk about maybe in a few weeks. But let me skip that for now. There's a notion of relevant, marginal, and irrelevant operators in quantum field theory. But this is a QFT statement, so I'll leave this to later on. Then I'll talk about it. Right? So QED, quantum electrodynamics, is what we call a renormalizable theory, and what you find is that a four-dimensional renormalizable theory of quantum electrodynamics will look like this, right? So in fact, now we know that the full QED is just psi bar plus I d slash minus m psi, right? So this is QED. This is the electron, and so I may as well write E, right? E for electron. And this is the Maxwell field, right? And there's an A here that couples, there's a A mu, J mu here inside this guy. And that's it. If you want to write down Lorentz invariant parity respecting four so U1 symmetry. So U1 symmetry is what I actually mentioned already. So So by U1, I want to say I'm now talking about global U1 symmetry, which means that I'm going to take psi, which is my 4-component Dirac splitter, and I'm going to replace it with psi times a phase. But now my phase is going to be a constant. Okay? I'm not going to let it be space-time dependent. The nodal current of gauge symmetries will depend on this arbitrary function. So I don't know what to make of it, right? So I may not care about that. But for constant data, we'll see that we can talk about it quite easily. So if you take psi and rotate it by a phase, like I said already, in this case, you also have to rotate psi dagger, right? Because this is just a complex conjugate right guy. So this must go by e to the minus I theta. So it should be clear that the Dirac Lagrangian, so the Dirac Lagrangian, which is psi dagger gamma 0, and then I d slash minus m psi, there's a psi dagger psi. So it should be clear that this is manifestly U1 invariant. I hope that's clear, right? Because this guy will give you this space if you make this replacement, and this guy will give you this space, but this guy and this guy will cancel each other out, right? But now we will see if we impose the Dirac equation, then we'll find that there's a non-trivial current that will come out of it. Okay, so let's do that. Okay, so let's do that. So let's now rotate the Lagrangian by this phase, but let's in fact impose. Let's remember that. Let's impose to the Dirac equation. So here we go. In fact, I don't have to do the full guide. I just need to do it. I just need to do the infinitesimal guide. Right. So this is psi plus I theta psi. Just up to first order in theta. Right. And this guy will be psi dagger minus I theta psi dagger. Right. And so let's do it. So what we have is I will vary psi dagger, and that gives me minus I theta psi dagger, and it will be gamma 0 d slash minus m psi, okay, plus psi bar I d slash minus m psi, and I'm going to vary this guy, but the variation is just going to give me plus I theta. Okay? And as you expect, of course, it's going to cancel out the 0, right? So it's 0. It does cancel, but we're going to do some manipulations with it to see what happens. Right now, it's just completely trivial. It's just a completely trivial statement, right? But because it's 0. But now we're going to do the following. We are going to now essentially integrate by parts one of these guys. Okay? We can choose either one of them, but let me just choose this guy here. So I'm going to use the Dirac equation for just give me 1 second.
When we shift the phase, it not affect the equation of motion.
Yeah, that's right. That's right. In fact, you can see it quite regularly, right? This is just minus n psi equals 0. And you multiply this by the phase, it just factors out like that. Remember we're doing global U1, right? So it doesn't affect at all. Yeah. Do you have a question? Yeah. Okay, so let's do it. Okay, so now I'm going to impose a Dirac equation on this guy. Remember, Dirac says that this guy is 0. Of course, you can say that this is 0 as well, but I'm going to actually integrate by parts. Okay, so what I'm going to do is the following. I'm going to say that this is I theta, and then I'm going to write this as partial mu psi bar I gamma mu. There's a gamma mu here, psi, and then the rest of the terms I'm going to. So I have this. I write this down, so I must cancel out this term here, psi bar I gamma mu psi. Okay, so that will still give me back this term, and then the rest of the terms will look like the following, right? Plus I theta psi bar I think there's an EA slash minus M psi term. Okay, and what's going to happen here is that we can now combine these two guys in the following way. Okay, this is now theta. This with a minus sign is I theta, and then again you discover that this is nothing but I d slash minus m acting on psi, and then you dagger it gamma 0 psi. Okay, so these two terms will combine into this. And I'm skipping the intermediate step because we actually did it already just now. That it's all just based on the fact that gamma 0, gamma mu, that product is Hermitian. And therefore you can write it as gamma mu dagger gamma 0, which then becomes this guy here. But then you have plus I theta partial mu, and then psi bar I gamma mu psi. So this is the Dirac equation. So again, this is 0, and you're now left with this guy is 0. So what have we gotten? We have found that the U1 Noether current can be identified with this object over there. Psi bar gamma mu psi. And the reason why is non-trivial is that this divergence-free property is not an identity, right? It's not a mathematical identity. It's not like you say 2 minus 2 is 0. It's not that. It's 0 only when you use the Dirac equation. So in other words, you have to evaluate this current on the solution. Otherwise, it won't be 0, right? So J mu, the reason why this is a physical statement, right? So the physics is that this guy is conserved when evaluated on the equations of motion. Meaning it needs to solve the Dirac equation, i.e. because we've used it, right? We've used it once here, and we've used it another time here. And only then we found that the divergence of this guy is 0, which means the divergence of J is 0. Okay? So that's very important. So if you learn a bit of, you learn GR, if you learn a bit of GR, you will also recognize something similar in GR, which is that the stress tensor of matter is not, in fact, identically divergenceless quantity. Right? So this is a side remark. So those of you who have learned a little GR will recognize that this needs to be true. But this, like the current in electromagnetism, is not an identity. Right? So if you learn Einstein's equations, you learn that the Einstein tensor is divergence free. This is an identity. Which means if you're very strong in calculation, just work it out. And you'll find that all the derivatives will cancel out and you get 0. There's no content in this, in fact, in some sense. It's just an identity. But this guy has content, physical content, because it's not always true. It's true only when you use the equations obeyed by your matter. Then you'll find that your stress tensor is conserved. Otherwise, it's not true. Right? So this is also true only when, I shouldn't say only when, the logic is when equations of motion are satisfied. This part. Whereas this is an identity. So this is a parallel that is worth noting because that's where the physics is. Okay. And this is, again, let me just emphasize, this is in fact, the reason why we call it nota is because this is an example. This is the U1 example of something very general called Noether's theorem. I think it's supposed to be called Noether's first theorem. I think she proved a number of theorems. I don't know what the rest are, but this is the most famous one. Noether's first theorem, which is the statement, let me just write it down, which is that the general statement is that whenever there is continuous symmetry, there exists a corresponding conserved current. When equations of motion are satisfied. So this is a general statement. All we're seeing is the U1 example of that. And in fact, let's do more. Because this is an important concept. So let's do more examples. Any questions for me? Okay. So let's do.
So it means
Yeah.
there is also the symmetries strategies.
This one? This one? Yeah. So for Einstein is general covariance actually. It's a bit tricky, but basically it's general covariance. Yeah. In other words, if your action is a coordinate scalar, then you will discover that your matter stress tensor should be conserved. But on shell, right? On the equations of motion. Actually, there's also a similar proof for the Einstein tensor. Although in that case, it's not, you don't have to use the equations of motion, it will just be true. Right? Yeah. Okay. Yeah.
This curve has some, has some physical corresponding variable that we can show.
Which current? Which one? U1?
Yeah.
That's the electric current.
Oh, I see.
Right? That's the electric current. Yeah. It's a number current. If you don't multiply by the electric charge, it's also the number current. Right? But also the electric current.
But does it work for the Dirac equation if we take out the U1 symmetry?
It comes basically for free. The reason is because when you want to construct Lorentz invariant objects out of spinors, they would have to usually occur in bilinears. You always have a psi dagger and a psi, right? Because you need to form a Lorentz invariant object. You can't have a standalone psi, right? It's a four-component spinor. You also cannot have a standalone psi dagger because it's a four-component object. So you have to find a way to combine them together, right? So usually you'll find that these guys, the U1 symmetry comes for free. Yeah. Okay. So one other thing I want to talk about is the chiral symmetry. Okay. So we talked about the gamma 5 and how you can use it to project out either the left or right-handed, left and right-handed part of the Dirac spinor. So because we've done the SL2C transformations, we can run it down in two ways. Where we can either transform. In other words, you can either multiply the phase to the left-handed guy only, or to the right-handed guy only, right? So far what we've done is we have only done it for the full Dirac spinor. But in principle, you can do it for the left and right-handed guy as well, right? So let me write it down and just remind you guys what I'm talking about. So the Dirac Lagrangian, remember, left-handed I, D, sigma bar dotted with D, left-handed, right-handed, and then the mass term. So it should be clear that if I do a sign, what I did just now can be basically split into the two cases, right? Psi left goes to e to the I theta psi left, and simultaneously psi right goes to psi right times e to the I theta. Okay, so this is equivalent to these two things. But if you don't have a mass term, you see, the mass term is what mixes the left and the right. So if I did it only to the left or only to the right, then the mass term will not be invariant under either one or the other. Okay? But if I have a massless, so if mass is 0, then you see that L is in fact invariant if I do psi left to the I theta psi left, or is or, not and. Right? Because if I do this, it's going to only touch this guy. And if I do this, it's only going to touch this guy. But there's a side dagger side, side dagger side. So as long as I don't have this term, when m is 0, these two guys are going to be invariant under either this or this. Okay? And that's called the chiral phase rotation. Right? So these are the chiral phase rotation. Because it only touches either the left or the right handed. And if you run it in terms of the if you run it in terms of the if you run it in terms of the, there's a way to write this in terms of the gamma 5 matrix. let me try to write that down. There's a way to phrase this in terms of gamma phase 5 matrix, which is that instead of doing this, I can instead look at what happens if I rotate the Dirac spinner in terms of e to the theta gamma 5. Right? So this is now back to the 4-component guy. Okay, so remember that this guy is anti-commuting with gamma mu. So if you look at, for example, the last term, so let me emphasize, this is not quite the same as this, but I claim that you can use this to basically implement a current that will give you a combination of this chiral symmetry and the full vector current that we got earlier. So if you do this, this is in fact not invariant. Okay, how do you see that? Because what will happen is that if you take gamma 0, so this will become e to the minus psi dagger e to the minus I theta gamma 5. Okay, gamma 5, by the way, is just minus I, minus identity and plus identity. So it's a Hermitian matrix. So when you take the dagger, it just gives you, it just flips the sign of this I, gamma 0, and then e to the I theta gamma 5 psi. So what will happen is that remember that this anti-commutes with this guy, and you can think of this as a Taylor series, right? So if you try to commute through every Taylor series of even powers, would give you back the same thing, but the odd powers will pick up a minus sign. So you will discover that this is basically e to the minus I theta gamma 5, and then when you commute it through, it will become minus I theta gamma 5. Gamma 0, psi dagger, minus n. Right? And this is not invariant. You don't get back itself. But if you have two of these guys, then it will be invariant. So in fact, these guys, psi bar d slash psi, this part is psi dagger gamma 0 gamma mu d mu psi. Under this rotation would go to psi dagger e to the minus I theta gamma 5 gamma 0 gamma mu d mu e to the I theta gamma 5 psi. So because there are two matrices, when you commute this Taylor series through, there will be no sign, there will be no, you don't incur any signs because there are two of them. So therefore you will actually cancel out and you will get back psi bar I d slash psi. Okay? So this part is invariant. Okay. So maybe I won't write it, I won't go through all the steps, but you can show that the current, that the local current of this guy is actually, so the local current for n equals to 0, because remember, when n is not 0, the Lagrangian is not invariant, so there's no local current to talk about. But when n is 0, you will find that the local current, corresponding local current, is in fact psi bar gamma mu, gamma 5 sun. That is in fact the pseudo current that we were talking about just now. Okay? But again, remember this needs to be for the massless case. And what you discover is that when you take the divergence in the massless case, this will be 0. Okay. Now, the funny thing is that this is only at the semi-classical level, conserved only at semi-classical level. Meaning, what I mean by that is that if you solve the Dirac equations, you plug in the solutions for the massless solutions, and you take the divergence, and you find that it's 0. But it turns out at the quantum field theory level, this is not conserved. This is something called the anomaly. This is called the QFT. The field QFT is a chiral anomaly. And chiral anomaly just means that this chiral symmetry that we have just talked about is no longer true, in fact, at the full quantum field theory level. And this, the easiest way to think about this, I think, is through the path integral. So I'll wait for a few weeks before, hopefully I'll remember, and I'll say this briefly. Basically what happens is that the path integral just as when you do an integration and you do a change of variables, you need to make sure you remember your Jacobian, right? So in the path integral form of QFT, it's the easiest way to see why this symmetry is no longer there. And it's because when you do a path integral over your fermions and your gauge fields and so on, when you do a chiral rotation of this form, you would also need to do a Jacobian in your path integral. And that Jacobian turns out to be not invariant under the chiral rotation. So it's a very subtle point that shows up when you do analysis of symmetries in quantum field theory. It's not enough to check that your Lagrangian is invariant, because that's the classical, basically the classical limit. You have to make sure that the Jacobian that you do in your path integral is also invariant, and that is a point that is worth remembering. So we won't have the time to talk about it in great detail, but at least you've heard it from me, right? So classical symmetries can be broken quantum mechanically. So if those of you who are regular attendees of our high energy fundamental theory group seminars would recall that there's this guy who worked on this duality symmetry of Maxwell's equations, right? And it turns out that there's an anomaly there as well. So it turns out that even though classically you can rotate 0, but obviously you can watch the Python decay, and so something is wrong, right? So later on people realize that it's because of the non-conservation of the chiral current. Yeah, there's a bunch of different names. If you just look up Python decay or the triangle anomaly diagram, there's also, I think there are a bunch of names associated with this particular one. It's called the ABJ ABJ anomaly or something like that. Adler, JQ, ABJ. B is Bardeen. Yeah, maybe Bardeen. Not 100% sure, but Adler, Bardeen, and JQ probably. These are all very famous field theorists. ABJ, I think. Oh, Bell, thank you, Bell, yeah. Yeah, Adler, Bell, JQ, right? Okay, so let's continue with scalar fields. Just a little bit. I know I'm almost out of time, right? But let me just go on just a little bit. So there's a similar discussion, or maybe let's do this because I only have a few minutes. So in your homework, not this current one. I don't think this current one. Maybe the next one. You would actually do the Juvenile symmetry for scalars, right? And so it's just to show you that it's not just a Dirac spinner that can be electrically charged, right? The first thing you want to do when you want to give a charge to something is to make it complex, right? So if this is real, then certainly you cannot consistently couple to electromagnetism. Because electromagnetism at a fundamental level, like I said, is associated with local U1 gauge symmetry. So what you will discover in your homework is there's a very famous basic model called the Abelian-Higgs model. And this is supposed to be a toy or simplified model for superconductors, actually. And what you will discover is that in the Abelian-Higgs model, you have a complex scalar. And like I said, you need it to be complex because you want to impose local U1 gauge symmetry on this guy. And so what you want to do is you want to construct a Lagrangian, right? And what does a Lagrangian look like? It has to have derivatives. It's a scalar, so you need two derivatives. So you take a derivative of phi, but because you want U1 gauge symmetry, you want to apply the covariant derivative on phi. And so to form a real Lorentz invariant object, that's the first thing you write down, right? The derivative and the complex conjugate, and then you try to contract them together. But to have a non-trivial dynamics, you want to also add a potential. And usually what people do is just add a potential that is also U1 symmetry. So this is now the complex conjugate of it. And usually what people do for the potential is that they introduce the baby version of the Higgs potential. That's why it's called Abelian-Higgs. So this will look like lambda plus lambda over 4. Lambda is real. And then it will be phi squared minus nu squared. Okay, so if you think about this, this is basically a what they call a Mexican hat, right? So if you think about it in a two-dimensional, because phi is complex, you can think of it as a two-dimensional plane. If you write down as phi equals to phi 1 plus I phi 2, then on the 1-2 plane, you can plot this this potential, right? And it looks like a it looks like a Mexican hat. Right? I'm not a very good artist, but basically the minimum, you should think about where the minimum is, and actually you will discover that it is actually the circle of radius nu. Right? And so in this homework problem, you will discover how to construct a local U1 gauge invariant scalar field theory, and you'll discover also this is the baby example of spontaneous symmetry breaking. It sounds very fancy. The name sounds very fancy, but what you discover at the end of the homework is that by this interaction, the complex scalar being electrically charged, and by virtue of having a potential that is a circle around this, that gives you this minimum, is able to give the photon a mass. Okay? So that's the physics behind spontaneous symmetry breaking in the Higgs, for the Higgs model, which is that it gives you a way to preserve the gauge symmetry while at the same time giving mass to the gauge field. And this is what you will discover in your next, I think it's not this homework, but I'm going to give it to you in the next homework. And you'll discover what the mass of the photon is. And in this abelian Higgs model, the mass of the photon, I believe, is exactly related to the skin depth in the Meissner effect. Right? So if you guys know, if you have a superconductor, I think it's a type 2 or something like that. I'm not sure that I'm getting it right. But one particular type of superconductors repels magnetic fields. And the skin depth is exactly related to the mass of the photon in this model. Okay. Any questions for me?
I just want to make sure the Dirac symmetry just we have multi-value ground state.
Yeah. So to be clear here, actually, I don't like the word spontaneous symmetry breaking because actually nothing is being broken here. Even at quantum level, I don't think anything is being broken here. It's called spontaneous breaking just because it looks like it's being broken, but it's not really broken. That's why they use the word spontaneous symmetry breaking. It's not really, nothing really is broken. The symmetry is still there, except that it's written in a way that looks like you broke the symmetry. Yeah. There's a more formal way to write it, but that will take QFT. You know, there's some statement about the vacuum and so on, but at the level of the Lagrangian, all that means is that this is invariant, right? But then what you realize is that if you expand, what you're going to realize is that when you expand the field about the minimum, if you rewrite the variables in terms of expansion about the minimum of the potential, then the resulting Lagrangian will not look invariant. And in fact, you will find that the photon will take up a mass term. And because of that, it looks not invariant. So it looks like this, right? So your mass, your photon has this kinetic term, right? And if I just gave you something like that, m squared a mu, then you say, oh, I broke my U1 gauge symmetry, right? If I just gave this to you. But it actually depends on where it comes from. If it came from a model like that, actually the whole thing is still symmetric. It's just that when you look at it this way, it looks non-symmetric. So that's what's going to happen. You will discover how to read this guy off. You will find that the m squared will depend on the lambda and the nu. Yeah. Okay, see you guys next week.